Hi, in this lecture I will be focusing on the step-by-step design of digital IIR filters, which are infinite impulse response filters. So we can start from the introduction. Basically, the procedure of designing a digital filter is similar to an analog filter design. There are some slight modifications in the design steps of the analog filter by which we can do the designing of the digital filter. So there are basically two ways by which we can design an IIR digital filter. One way is the impulse invariant design, and the other one is the bilinear transformation. In the impulse invariant design, we follow the normal method of the analog filter design with slight modifications, and once we acquire the transfer function of the analog filter, we can do its inverse Laplace transformation into HT, and then we can do its Z transformation into HZ. In this way we can acquire our digital filter transfer function, which is Hz from Hs, by using this method of impulse invariant design. While in the second method of the bilinear transformation, the rest of the method is the same, where we acquire the Hs after slight modifications in the steps of the analog filter design, and once we acquire Hs, then we can directly use the bilinear transformation to transform it from Hz to Hs to Hz. So in impulse invariant design we do Hs to Ht inverse Laplace transformation, and from Ht to Hz, and in bilinear transformation we do the direct transformation of Hs into Hz. So these are some two methods of designing some digital filters. Basically we have two major classes of the digital filter. The first one is the infinite impulse response filter, and the second one is the finite impulse response filter. In this lecture we will be doing discussion on only the design procedures of the IIR filter. The rest of the lectures we also focus on FIR filter. Now if we want to do some study of the theory of the infinite impulse response filter, let's have a transfer function which is Hz over here, and in this transfer function we have this equation. We are having a scenario in which we will be given this transfer function, and you will be asked to do the realization of the filter. What is the realization of the filter? It is actually with the help of transfer function of the filter how you able to form a convenient equation from that transfer function equation, and then use that equation to do the realization of the filter, which is the diagrammatic representation of that filter. So here we can understand this step. If we have designed an IIR filter by the previous steps as we have discussed in previously, then we will be having this equation, this transfer function equation. We will be using it and do the realization of the filter. How we will be doing this? We know that Hz is equal to Yz over Xz, output over input. Do the cross multiplication, we got this equation, and then we multiplying it inside the Xz, also inside, and then afterwards we are doing the inverse Z transformation by using the time shifting property of the Z transformation, and we transform that equation into this equation, where we have the present value of output, the delay past values, and the present value of input and delay past values of the input, and we rearrange this equation by having output on one side and all other values, all other terms on the right hand side. Then we can do its realization, which we will be discussing in the next lecture of how we will be using this equation, and with the help of this equation we are able to construct the graphical design of the filter. Now we have two kinds of behaviors in the filter. One is the recursive behavior, which is the feedback behavior, and other is the non-recursive behavior, which is the non-feedback behavior. IIR filter are normally feedback filters, so they are recursive filters which are having a feedback loop in their design, in their realization, while the FIR filter are non-feedback filters, and they are also non-recursive filter which are do not have any feedback input. Feedback input is normally a kind of output which is in a delay version and which is given at the side of the input along with the original input or delayed inputs of the filter. Now we are again revising our concept that once we get the HS of how we will be proceeding afterwards by using two methods. One of them is the impulse invariant transformation method, and the other is the bilinear transformation method, and from HS we acquire HZ by any of these two methods. These both methods are applicable for the Butterworth and Chebyshev approximations of analog filter. Basically, for the design of the digital filter, we follow, for the IIR case, we follow the design procedure of the analog filter with slight modifications. We will be discussing that modification in our future problem. And then after we acquire HS, we will be applying any of these two methods to acquire our HZ. So in impulse invariant transformation, let's suppose we have this kind of transfer function of the analog filter arrives. Then we will be doing its inverse Laplace transformation to acquire it in the time domain, and then we will be doing its Z transformation in order to acquire from HT the HZ. So this is a demonstration of impulse invariant transformation method. Now we will be looking at this example in which we have a transfer function of the digital filter IIR filter, and we are able to do the design, we are able to do its realization in this way. So before doing its realization we have to follow some steps. We will be looking those steps that we know HZ is equal to YZ over XZ. So we will be doing the cross multiplication, we will be doing the inverse Z transformation, and then we are moving yn on one side and all other terms of the equation on the right hand side, and then we will be using this equation and we will be constructing this diagram. And in this diagram you can see that we have on the right hand side the yn, on the left hand side the xn, we have a summation sign, and this z -1 is indicating the delayed yn minus 1, which is multiplying by a multiplier of 0.368 and summating in the summer along with the original input. So we can see from the equation which is having this kind of behavior, and that kind of behavior is replicated in the realization of the filter with the help of the z negative and the summation element over here. So this is how by which we can do the realization of the filter, and we are following these some steps and getting some equation and rearrangement, and then using the delay element, the multiplier, and the summation element in order to do the realization of our equation of the IIR filter. We have another example over here in which we have this kind of transfer function of the digital IIR filter, and we are following the same steps as we have done over here, y over x, doing the cross multiplication and getting this kind of equation over here after the inverse z transformation, and having yn on the left hand side and all other terms on the right hand side. And then we are using this delay element, the multiplier, the summator, and these two delay elements and the multipliers over here and getting this equation's realization. As you can see from this diagram and from the previous diagram, this one, that we have a kind of feedback loop. So this is basically a digital IIR filter, which is a recursive filter. In the FIR filter, this feedback from the output doesn't happen. Okay, so now we will be focusing on the step-by-step design of the Butterworth digital IIR filter by making use of the first method out of the two, which is the impulse invariant transformation method, in which we first do the analog filter designing and then to acquire HS, and afterwards we are doing its conversion into HT and afterwards into HZ. So in impulse invariant design we will be following this way, and we are having some additional uh, enhancements in the analog filter design as well, because in this method we are following some modifications. We are having some additional step compared to only analog filter design, and that step has to come into play. So once we acquire the HZ, we can able to construct the design of the digital filter as I have discussed previously. Now we have an example in which we can understand this all steps. Uh, it is saying that we are having a Butterworth digital low pass filter with these values, in which we have the sampling frequency, we have the two frequencies over here, we have this passband gain, which is H1W, and this is H2W over here. Okay, so what we are doing over here is that we have an additional step of the normalization of the frequency compared to analog filter design. First of all, we have to do this step. In this step we are doing what? We are transforming our F1 and F2 into W, and also we are doing the sampling as well and using that sampling frequency. So we are using that formula. Normally the formula of W is 2 pi f, but over here we are doing the sampling as well, so we are dividing it with the Fs. So we are using the F1 and F2 like that. We are using the F1 and F2 and we are calculating the normalized frequencies by dividing it with the sampling frequency, and we are getting W1 and W2. So this is the first step, which is the normalization of the frequency. Now the second step is that we already know the Butterworth filter uh, mathematical model over here. We are having two values of H1 W, H2W, and W1 and W2. So we are putting H1W and W1 once in that formula, and then H2W and W2 another time in this formula. So we have two kinds of equations and we are simultaneously solving those two equations, and we are getting our unknown values, which are N 1.98 rounded to 2 and WC, which is 0.737. So we have acquired our N and WC. This is the second step, and it is the same step which was involved in the design of the analog filter. Okay, so now we are going to determine the poles and the valid poles for the Butterworth case, which model we are following. So we know that we have n is equal to 2, so we have 2n to calculate the Butterworth poles, which is 4, and we have to calculate the angle between those by this formula. 360 divided by 2n, we get 90 degree, and we have to calculate the valid poles, which can be calculated by this Euler formula over here to calculate the conjugate poles, as we have discussed in the previous lecture of the analog filter design. So we already know that we have n is even, so the first pole location will be at theta by 2, and then the remaining poles will be according to the formula as we have discussed in the analog filter design. So we have two poles and we have done their calculations as well, and we have the valid pole calculation is already done for us. Now we have to calculate the HS, and we already know that the transfer function for a second order filter is this kind of transfer function, in which these are having some unknown values of A and B over here, and we will be putting those two pole values over here, and then we are doing its inverse Laplace transformation to get HT, and then we are doing its Z transformation to get HZ. So this is all the methods which we have to follow in case of IIR digital filter design by using the Butterworth model uh, for the impulse invariant method. Okay. So now we will be focusing on the bilinear transformation method, in which we will be using, we will be calculating the transfer function of the digital IIR filter. So firstly we have to know that bilinear transformation is actually the direct conversion of HS into HZ, and for conversion we use this kind of equation, which is a transformation equation in which t is the sampling time. Once we follow all the steps as we have discussed in the previous problem uh, of the IIR digital filter design of the impulse invariance method, we once arrive to HS, we will be using this equation to transform it in from HS to HZ directly, and we also have to do some extra process in the previous example, and we have to convert W's into omegas, and we will be using these kind of omegas instead of W's. This is a condition which has to be fulfilled for the bilinear transformation if we have to use that transformation equation. Let's see how we will be doing this. So uh, before we do this, uh, let's have some example in which we have HS and we want to convert it by using bilinear transformation into HZ. Then we will be using the transformation S, which is the transformation equation. We have put uh, in place of S that transformation value, and then we have done the rearrangement by simplifying, also taking t is equal to 1, and then after rearranging we have converted with the help of transformation equation of S, we have with the help of bilinear transformation converted the HS into HZ. Okay, so now we have a problem in which we will be using the bilinear transformation method. So we will be following all those steps. Uh, we have an IIR Butterworth filter with H1W this, we have H2W this, and we have the frequencies, and we have the sampling frequency as well. So over here what we are doing is that we are over here first normalizing the frequencies, and for the normalization of the frequencies we already know these two formulas, and we have used the sampling frequency and both the frequencies over here, and we have calculated the W1 and W2, and then afterwards we have another additional step for which we have to do the because in this problem we have to do the bilinear transformation. So for that bilinear transformation we have to do that extra step. So this is the conversion of W's into omegas. For we are using these formulas, and we have put over here those formulas, and we have put their values over here to calculate the omega. So we have converted the W1 and W2 into omegas by putting all these values over here. Now we will be doing the determination of n and omega c's based on the Butterworth model. We know the Butterworth mathematical model. We have 1 omega, and we have 2 omega, and we have h1w, and we have h2w. So we have put h1w and omega 1 in one Butterworth equation, and in the same Butterworth equation, another Butterworth equation, we have put the h1w and omega 2. We have two equations of the Butterworth approximation, mathematical model, and we have simultaneously solved those two to get the unknown values of n 4.25 round off to 5 and omega c. And with the help of those values, after which we have another step, which is the same method, same step like the in the previous problem of the impulse invariant transformation. We have uh, to calculate the poles, Butterworth poles. 2 multiplied by 5, total Butterworth poles 10, and the angle between them is by this formula. 360 divided by 2n is 36 degree. So we have this an odd value. The placement of the first pole will be on the x-axis, and the remaining poles will follow the circle. And we are to calculate the number of valid poles, which are 5, and we have, with the help of Euler formula, calculated their values. And we already know that this is a kind of HS equation for the transfer function of the analog filter, in which we have to put these unknown values of the poles over here, and we have put their values of unknown values of the poles over here. Now we got this equation. Now just to simply put the value of s is equal to this thing with t is equal to 1 in that equation to get our hz equation. And this is all about the bilinear transformation method, and we have got the hz, which is the digital IIR filter design based on the bilinear transformation method. Now we have another kind of process which is known as frequency transformation, and this is a way by which we can calculate the unknown transfer function of the filter from a known transfer function of the filter. Normally when we do the designing of the filter, we are to calculate the low pass filter transfer function, and if somebody says to calculate the high pass filter transfer function from that transfer function of low pass filter, then you able to use the frequency transformation to do that kind of a thing. So it is basically a conversion process. So once the transfer function of the low pass filter is found, we can able to calculate the any other transfer function of any other filter from that transfer function of the low pass filter with this frequency transformation method. So let's suppose we have a low pass filter, and in that low pass filter, this is the transfer function of the first order low pass filter. We do this kind of arrangement, and we do this kind of approximations. Then we know that x is equal to s over wc, and then we do the rearrangement. So we know that this is a low pass filter uh, frequency transformation uh, uh, kind of operator, or you can say it is a kind of once we get any kind of transfer function. Let's suppose we have a high pass filter transfer function, we have to convert it into this form of x, and after that, if we want to acquire the low pass filter transfer function from that, we have to replace the value of x with this value, and we will be able to get the low pass filter transfer function. Same is the case for the high pass and low pass. Now we have a high pass frequency transformation. We already know that high pass first order high pass filter has this kind of transfer function. We do this kind of arrangement. You can correct it. It is S over W over here. So we have this kind of rearrangement approximations, and we have transformed it into that same standard expression of 1 over 1 plus x, and we have this kind of operator. When we put this kind of operator approximation in this, we get the transfer function of the high pass filter. Let's suppose we have a low pass filter transfer function given. We have to first transform it into the x form, and then we have to put that value in that to get the high pass filter transfer function. So we can normally say S is equal to WC over X is used for the high pass frequency transformation. We have an example over here in which we have the first order high pass filter transfer function, and we are to acquire a low pass filter first order transfer function. From that, we have used the equation of the high pass filter, and we have used the equation, sorry, we have used this equation of the low pass filter which is given to us, and we are to calculate the high pass filter transfer function. From that, we have transformed it into this form, and then we have used this kind of uh, approximation in the 1 over 1 plus x, and then we have got the first order high pass filter transfer function over there. Thank you very much.